Rational functions are they're just fractions. Rational is another way of saying fraction, something like a over b. Except for the things we're going to be playing with aren't as simple as a over b. A is probably going to be a polynomial function, and b could also be a polynomial function. So previously in 3.1 and 3.2, we were dealing with just a, like a polynomial in the numerator. And when we did that polynomial in the numerator, we found out a whole bunch of stuff about it, right? We found out like where the x-intercepts were, where the y-intercept was, where it had even multiplicity and odd multiplicity, and we were able to graph it and do all kinds of stuff like that, okay? So now what we're going to do is we're going to add another layer of sophistication to this by placing something in the denominator. And this now makes it a rational function. Let's start out with maybe the simplest rational function. If we said f of x is equal to 1 over x. And so how does this behave? What does the graph look like? And there's the graph. Where does it go through the x-axis? It doesn't really go through the x-axis anywhere. So what happens as x approaches, so if we go back here and we say as x approaches negative infinity, what does the function approach? So as x approaches negative infinity, as it goes this way, what do the y values approach?
0.
Yeah, they approach 0. And if x approaches positive infinity, what does the function approach? So again, if we go off this way, the function approaches 0 as well. All right, so that's cool. What about when x approaches 0? And we have to be a little bit more specific about when x approaches 0. We have to say, because here's 0, right there at the origin. Is it approaching 0 from the left? So is it coming in from the left? In which case we'd say x is approaching 0 from the left, and we'd put a little negative sign by the x, saying that means it's coming in from the left. Or is x approaching from the right, coming in from the positive x-axis? And in that case, we'd have an x with a plus up in that corner. So as x approaches 0 from the left, as this graph gets closer and closer and closer to 0, what does the y-coordinate approach? Negative infinity. And as x approaches 0 from the right, as it comes in 4, 3, 2, 1, 0.5, 0.3, 0.1, the function itself approaches positive infinity. So what we have here in this case is we have something called a vertical asymptote. An asymptote is an imaginary line that the function approaches but never crosses. And we have a vertical asymptote right at x equals 0. There's a vertical asymptote there. And why is there a vertical asymptote at x equals 0? Because of this. Because remember, you can never have 0 in your denominator. The role that the denominator plays is it identifies the location of vertical asymptotes. Asymptotes that run up and down. So that's what we want to look at today, is these vertical asymptotes. So let's take a look at a couple problems. So first of all, we're going to start out with these problems, and all we want to do is run you through some mathematical gymnastics of factoring, of simplifying polynomials that have a numerator and a denominator. So for this first one, we have x squared plus 11x plus 30 divided by x squared plus 6x plus 5. And what we want to do is unfoil or factor these polynomials. So if you take the first one, we can break that into two monomials, an x and an x. And now you have to play this little game in your head where you look at factors of 30, and you need factors of 30, two numbers that multiply to give you 30, whose sum is 11.
6 and 5.
6 and 5. So we're going to say x plus 6 and x plus 5. And if you're ever in doubt, run your answer backwards. Like actually FOIL this out and show that you get that middle term, 11x. but this works. And so that means we have x plus 6 and x plus 5. Now let's also FOIL the bottom. So we're going to FOIL the bottom number, or the bottom polynomial, x and x. And again, we're looking for factors of 5 whose sum is 6. And it's going to be 5 and 1. So we'll say x plus 1 and x plus 5. And then check this out. We got an x plus 5 and an x plus 5. And those chunks, that entire thing inside parentheses, cancel out. So this cancels with this. So we're left with x plus 6 divided by x plus 1. Now, can we cancel these x's? There's an x in the top and an x in the bottom. Can I cancel them? Why not? Because they're adding. Yeah, when you cancel them, you're actually doing a division, right? And division only does multiplication. So if it was x multiplied by something and x multiplied by something, you cancel. But you're exactly correct. Because it's addition, we can't cancel these. A lot of times students think that just because there's something in the top and something in the bottom, you can cancel them. And that is not true. It's only true when you're multiplying stuff. For example, 2x divided by 3x. Or even better yet, let's do this. 6x divided by 1x. Can I cancel these x's? Yes, you can. Because they're multiplied by the 6 and they're multiplied by the 1. But just because something's in the top and the bottom doesn't mean you can cancel it. And here's a good example. What is 24 divided by 2? 12? Do you think it's 12? How did you get 12? You think it's... No, the answer is 4. Because all you have to do is cancel these 2's. No, this isn't what you do, right? And you all know this, right? You're like, oh my gosh, he's right. You know, this is the idea. This idea here of canceling 2's is the same idea you're trying to pull off here. You can't do it. You know 24 divided by 2 is 12. Yes, it's 12, okay? But for the sake of argument, I'm trying to show you sometimes people just start canceling stuff because it's on the top and the bottom, and you can't do it. What matters is how it's put together. And Ariel, you're exactly right. These are put together with addition, so you can't cancel them. If they were multiplied, then you could, but because they're added to 6 and added to 1, you cannot cancel. And you know, this is a little bit of a silly example, but you would be amazed at how many students are fine canceling these 2 x's, right? It's the same idea. And so keep that in mind. You can't cancel these x's. All right, let's go to the next one. So the same idea here. In the top, the first thing you want to do when you're factoring is always ask, is there a number or variable you can factor out of every term? And in this very top one, there is a variable we can factor out. We can take an x out of everything. So that'll be x squared plus 9x plus 20 divided by, and here we could also factor out an x. So we'll say x times x plus 4. So the first thing we did was factor out a variable. And can I cancel these 2 x's? Yes, you can. Why?
Because they're multiplied.
Because they're multiplied by this thing. Yeah, this is x times and x times. And so that means these 2 x's can be canceled. So we're going to cancel them out. All right, so that's going to leave us with x squared plus 9x plus 20 divided by x plus 4. And now we need to FOIL the top part, or unfoil it. And so what are factors of 20 that give you a positive 9?
4 and 5.
Yeah, x plus 4 and x plus... And here's another thing. These problems are rigged. They want things to cancel out. So when you look at your denominator and you see an x plus 4 sitting in your denominator, chances are there's an x plus 4 in the numerator too that's going to cancel out. This helps build your intuition. Look around and see what else is going on in the problem that might be used to your advantage. X plus 4, x plus 5 divided by x plus 4. And then what happens? This x plus 4 and the x plus 4 in the denominator are going to cancel each other. Those entire chunks of stuff cancel, and you're just left with x plus 5. So this one is 4x squared minus 8x divided by x to the third minus 4x. Out of the top, let's factor out a 4x. Bless you. So that'll leave you with x minus 2. And then on the bottom, let's factor out just an x, I guess. And that'll leave us with x squared minus 4. Now that x squared minus 4 is a difference of squares. And this is going to factor into x plus 2 and x minus 2. What can cancel? I've got an x minus 2 here and an x minus 2 there. I've got an x here and an x here, so I can cancel those two. And so on the top, in the numerator, you're just left with a 4. And in the denominator, we're left with x plus 2. So we want to determine the domain and the vertical asymptotes for each of the following functions. This is what we want to do, and sometimes what helps with these is to graph them. So here's the graph. And you notice it kind of looked like the graph we had before. You know, it's kind of got this where it swoops up towards infinity one way and it swoops down towards a negative infinity from the other way. And if we zoom in on this guy, where does it appear that there's a vertical asymptote? Kind of like on this line right here, which happens to be x equals 3. So if we go back to this, look at that. So if we took that denominator, if we took 21 minus 7x and set it equal to 0, that will give us the location of the vertical asymptote. So you solve this. Negative 7x equals negative 21. X equals negative 21 divided by negative 7. X equals 3. That is the location of the vertical asymptote. So x equals 3. What is the domain of this function? And again, if you go back to the graph, what's the domain?
All real numbers besides 3.
Yep, all real numbers except 3. Because 3 is where that vertical asymptote is. So there's an imaginary line right here that the graph does not cross. If you want to think about it, there's an open dot right at 3. There's an open dot here where the function is not defined. The domain is going to be all real numbers. I guess we have to write this out. Write a sentence, huh? All real. If I could just copy and paste, right? So when you do this, just copy and paste that sentence right here and change x equals 4 to x equals 3 in our case. And that's the location of the vertical asymptote. All right, what about g of x? We do the same thing. So we don't have to graph this one. We can just say, where's the vertical asymptote? And so it'd be negative 2x minus 4 equals 0. Negative 2x equals 4. X equals negative 2. So what does this graph look like? I don't know, but I do know that there's a vertical asymptote at negative 2. And the graph is going to swoop up on one side and swoop down on the other side. Maybe I've got the swoops wrong. Maybe instead of swooping up, it swoops down this way and it swoops up this way. I don't know. But I do know that on either side of that vertical asymptote, the graph is going to skyrocket either to positive infinity or negative infinity. So take a look at this function. F of x equals negative 12 times the quantity, x minus 2 on the top, and x plus 3 and x minus 4 on the bottom. And what we want to do is we want to sketch this graph. Vertical asymptote. One is at x equals negative 3, and the other one is at x equals positive 4. So those are our two vertical asymptotes. So at negative 3, 1, 2, 3, we have a vertical asymptote. This is x equals negative 3. And then we also have one at positive 4. 1, 2, 3, 4. And this is x equals positive 4. The bottom defines your vertical asymptotes. The top are your x-intercepts. So the numerator gives you your x-intercepts. That's what we did yesterday with all the polynomial stuff, right? Like we gave you polynomials in factored format, You're like, where are the x-intercepts? So you just set them equal to 0, and boom, boom. That's what the top does. So this guy has an x-intercept at positive 2. And that is the only x-intercept. And this x-intercept, to build on what we talked about yesterday, has multiplicity of 1. So that is a pass-through. It's an odd multiplicity, so it's pass-through. So we have an x-intercept at x equals 2, and it's a pass-through. So what else do we need here?
Y-intercept.
Yeah, let's find the y-intercept. So for our y-intercept, and hold on, let me get fancy with the colors. Here's our vertical asymptotes. Here's our x-intercept, and then we'll do the y-intercept in blue. So for the y-intercept, you find f of 0, which is negative 12 times 0 minus 2 divided by 0 plus 3 and 0 minus 4. So that's negative 12 times negative 2 divided by 3 times negative 4. Zip, zip, negative 2. Is that cool? So 0, negative 2 is our y-intercept. It's going to go through that y-intercept, and then it's going to curve back up and go through that. Okay? Multiplicity is odd, so that means it's not a bounce back on the x-intercept at that point 2. It's odd multiplicity, so it's a pass-through. Now here's the other thing. Your vertical asymptotes also have a multiplicity. So that x plus 3 has a multiplicity of 1, and the x minus 4 has a multiplicity of 1. And what that means is, if we take this a sample of x minus 4, if we look at this guy right here, because it has odd multiplicity, that means if the graph approaches positive infinity on one side, it comes up from negative infinity on the other side. If this was x minus 4 squared, then the graph would come down on the same side. So multiplicity is really more about same side versus opposite sides. But this one's not squared. And so that means that this line comes, because the graph goes up to positive infinity here as it approaches from the left, that means it approaches from the right negative infinity. And then the same thing happens over on this guy. This half of the graph, as it approaches the asymptote from the right, goes towards negative infinity, which means from the left it goes up to positive infinity. There are no other x-intercepts, so that means this graph way over here on the right does not cross the axis, and this graph over on the left does not cross the x-axis. Here's another rational polynomial. X-intercepts are going to be negative 2, 0, and 2, 0. Positive 2, negative 2. So here are the x-intercepts. And both x-intercepts have odd multiplicity, so they're both pass-throughs. So negative 2 and positive 2. So they're both pass-throughs. Now let's talk about the vertical asymptotes. So you're going to have a vertical asymptote at x equals negative 1 and x equals positive 3. So here's the asymptote at negative 1. X equals negative 1. And that also is odd multiplicity. And we also have one at 3. X equals 3. So here's the other vertical asymptote. X equals 3. And that is also odd multiplicity. So we're pretty well set with this. The only other thing we need to know is where's the y-intercept, because that kind of gets the ball rolling as to how we're going to sketch this. So to find the y-intercept, we're going to say f of 0, and that's going to be 2 times negative 2 divided by 1 times negative 3. So that's negative 4 over negative 3, which is 4/3. So our y-intercept is positive 4/3. And again, kind of like yesterday we were talking, it really doesn't matter to the quantity. It's nice that we know it's positive 4/3. What we're really going for there is the sign. Is it a positive number or is it a negative number? And this is a positive 4/3, so I'll just put it right here. So now if we were to sketch this, it's got to go through the y-intercept, and then go through our x-intercept, and then go down here, right? Because it can't curl back up because there's no x-intercept there. The x equals 3 is odd multiplicity, which means if it goes down on this side, it's got to go up on this side. And then there are no other x-intercepts, so that means it's going to veer off and avoid that x-axis because it can't go through it. Otherwise, there'd be an x-intercept there, right? On the other side, the vertical asymptote x equals -1 goes to the top on one side, so that means it's got to go to the bottom on the other side, and it's got to pass through our x-intercept there. Now we're going to give you the graph, and you got to come up with the poly. F of x equals, start with the top. Remember, and we could almost do this. We could say x-intercepts are represented on the top, and vertical asymptotes are represented on the bottom. So we're going to say x minus 2. It's odd multiplicity, it's a pass-through. Yep, so odd multiplicity, so we're cool with just saying x minus 2. Any other x-intercepts? Nah, it doesn't look like it. All right, so we're done with that. On the bottom, vertical asymptotes. X plus 2, that takes care of this guy, and x minus 3. Now tell me about the multiplicity of x plus 2. It's odd, because it's a pass-through, right? Like, this is what you're talking about, the plus and the minus, right? They're opposite, the infinities are opposite signs. And what about the x minus 3? This is an even, it's a plus plus. So that means you have even multiplicity, so we're going to slap a 2 on there. There is one more thing we have to do with this guy. And that is, if you remember back on this one up here, way back here, there was this -12. Remember that? So there's a factor in front of this guy. There's an A sitting out here. Because if we threw this into the graphing software, we'd get the x-intercept right, but maybe not the y-intercept. We'd get the x-intercept and we'd get the vertical asymptotes, and we'd have the right structure, but maybe it's stretched up or compressed down. So we need to make sure we get that A right. So we know from this graph, this point here tells us f of 0 equals -1. F of 0 equals this thing, which has to equal -1. So we got to solve for A. So we'll say A times -2 divided by 2 times 9 equals -1. And all I did is I plugged zeros in for all these. So this became a 0, this became a 0, this became a 0. 0 minus 3 is -3. -3 squared gives you the 9. We can cancel these 2's and make it a -1. Multiply, so A is going to equal 9. So the complete graph is going to have a 9, or pardon me, the complete equation will have a 9 sitting out in front. Look at that. Cool. Here's another